algebraic terms. Prime numbers are always odd. We just need to find a counterexample to show this is not true. Okay? 2 is a prime number. Okay, and you actually have to write sentences. 2 is a prime number. 2 is even. Therefore, not true. The square root of a number is always smaller than the number itself. Again, this is false. If I pick a number, for example, the square root of a quarter is in fact a half. A half is greater than a quarter. Therefore, not true. If P is prime, then P plus 2 is prime. Again, this is false because if P equals 2, P plus 2 equals 2 plus 2, which equals 4. Now, this is something I want us to get used to. We can't just say 4 is even. Okay? What we need to do is factorise. 2 lots of 2. 2 is a factor, because 2 is the smallest even number, isn't it? Okay, 2 is a factor, therefore even. So 2 is a factor, therefore multiple of 2, therefore even. We need to get used to, especially in these first few lessons, when we are doing proof, we need to really understand what's going on. And then 2n squared plus 11 is prime for all integer values of n. So we've got to find a value for n where this is not true. Okay? So if I did 4 times 2 is 8, plus 11 is 19. Okay, that's not going to work. 3 squared is 9. 9 times 2 is 18, plus 11, 29. Did anyone get one? Not yet? Okay, there is definitely one. Let's try 4. I'm going to get 16, 32, 43. No. 5. What are we going to get? 50, 61. Okay. 36, 72, 83. 49, 98. 109? Is 109 prime? I think it is, isn't it? Okay, we will find a number. Let's put a star on that. We'll come back to that later. So, we have 2 types of proofs. We have even and odd proofs. Now, everyone should be happy reminding me, how do we write an even number in terms of algebra? An even number is 2n. An odd number, 2n plus 1, or 2n minus 1, or 2n plus 3, etc. Okay? So it says show that for any integer n. Okay, so we're talking about odds and evens here. N squared plus n is always even. So because we want to show for any integer, we need to think there's 2 possible cases. You either have odd numbers, you either have even numbers. So, for even numbers, we're going to have 2n squared plus 2n. 2n squared is 4n squared, plus 2n is plus 2n, okay? To prove that a number is even, we need to show that 2 is a factor. This is the same as writing 2 lots of 2n squared plus n, okay? It is clear to see 2 is a factor, therefore multiple of 2, therefore n squared plus n is always even when n is even, okay? Because we've said let n equal to n, okay? Then for odd numbers, we're going to have 2n plus 1 squared plus 2n plus 1. Because for odd numbers, we're letting n equal 2n plus 1. essentially. I know there's a lot of n's, but you know, we really have to think about what's going on. So what does this equal? 2n plus 1 squared, 4n squared plus 4n plus 1, plus 2n plus 1. This is going to give me 4n squared plus 6n plus 2. If I can take 2 as a factor, factorise out 2n squared plus 3n plus 1, and there we have it again. 2 as a factor, therefore multiple of 2, therefore n squared plus n is always even when n is odd. And then the final statement, therefore n squared plus n is always even for any integer n. Okay, so you can see there is a lot more writing, but you have to really stipulate what's going on. Okay. Right, you've got 2 questions to check your understanding. Okay, again, very similar to what we've just done. Off you go. Right, so the first one should be relatively simple. 3 consecutive even numbers. The first even number, 2n. The second even number, 2n plus 2. The third even number after this, 2n plus 4. So you can see these are my numbers, and these are 3 consecutive numbers. If it says sum, it means add it up, okay? If we add all this up, we get 6n plus 6. If we need to prove that something is a multiple of 6, we need to prove that 6 is a factor. So we need to factorise out 6, which is the same as 6 lots of n plus 1. Then we would write 6 is a factor, therefore multiple of 6. Okay, the next one says product. I'm sure we should all be happy when it says product, we are multiplying. Okay? Now, for those of you that, I know some of you have just said then, you know, you've struggled a little bit. If we just think about some numbers, 1, 2, 3, 4, 5, 6, 7, 8. Okay? And n, you know, like our nth term when we did sequences, okay? If we assume n is 1, how do we get to 2? We know that the 2 times table is 2n. Okay? How do I get to 1 from 2n? I need to minus 1. So this is 2n minus 1. Okay, then 3 would be 2n plus 1. 4, 2n plus 2. 5 would be 2n plus 3. 6, 2n plus 4. Okay, so you can see here we have 3 consecutive even numbers, 3 consecutive odd numbers. Okay, so you can decide, you know, which way round to use them. You might even want to go minus. Some people do 2n minus 2 as it's still an even number. You can do 2n minus 2, 2n, 2n plus 2. Okay, they're still 3 consecutive even numbers. So for the second one, prove that the product, so if it says product, the first thing I'm going to do is I'm going to write a multiplication sign of 2 consecutive odd numbers. So I need 2 numbers that are odd that are consecutive. So I'm going to choose 2n minus 1, 2n plus 1. They're consecutive odd numbers, okay? So 2n minus 1 multiplied by 2n plus 1. 2n times 2n, 4n squared, and then I've got 2n minus 2n minus 1, okay? So we know plus 2n and minus 2n, they do cancel, but you still have to write all of this. This is a proof. You can't leave anything out, okay? Even though in your head you know they cancel, when you're proving, you've got to show every step of your working. Then we're left with 4n squared minus 1. If something is 1 less than a multiple of 4, you need to get 4 as a factor, Okay, so this is equivalent to 4 bracket n squared minus 1. Okay, 4n squared, 4 bracket n squared is a multiple of 4, is a multiple of 4 because 4 is a factor. Okay, minus 1, this is 1 less than a multiple of 4. Therefore, proved. Okay? You know, if it said prove that it's 2 more than a multiple of 4, you would have to make sure you can factor out a 4, and on the end you'd have a plus 2. Because you want 2 more than a multiple of 4. So someone just said then, they used 2n plus 1 and 2n plus 3. So if we quickly do that, so I'm going to have 2n plus 1, 2n plus 3. So I'm going to get 4n squared plus 3 plus 4n. Okay? So 4n squared plus 4n plus 3. And it's 1 less than a multiple of 4. Now, this is where proof is magical and what I love about proof. Okay? The number 3. And this is why Pure 2 is really going to challenge us. How many ways could we write the number 3? The number 3, so we're going to pause right there, can be written as 2 plus 1. It can be written as 5 minus 2. It can be written as, and what we need is a multiple of 4. Hold on a minute. 4 minus 1. I know, mind-blowing. So, here we have it. Instead of writing 3, we know, because we have a multiple of 4, we want to take out a factor of 4. So, I'm no longer going to write 3. I'm going to write 4 minus 1, which is exactly the same as writing 3. Are they completely equivalent? Absolutely. So now I can carry on. So I have 4n squared plus 4n plus 4 minus 1. This now means I can take out 4 as a factor, n squared plus n plus 1 minus 1. And I can go back to our previous thing. 4 is a factor here, so this number is a multiple of 4, no matter what anyone says, because 4 is a factor. And then, it's 1 less than a multiple of 4. So whatever this multiple of 4 is, we're taking away 1. Now, this is the trick, and this is why maths is so beautiful. As long as, and I speak about this all the time with you, as long as it's equivalent, we can write it however we want. Okay? Okay, sorry, I got so excited then that you are right. This is 2n, this is 6n, this should be an 8n. Okay, there we go. I mean, it's still, the principle was the number 3, 4 minus 1. This is what happens when we get excited. But it's okay, absolutely right. Okay then, so how are we feeling? Okay, I would like you to try. So this is question 1 here is very similar, where you had to prove it's odd for all integers n. So you have to prove it's odd for even and for odd. Okay, so I definitely suggest doing question 1 if you struggled with that concept. If you were very happy, have a go at question 8. Okay, I'm going to give you all a minute. Okay, homework, questions 1, 2 and 3, please.
Which slide?
Slide 6.
We need to add it up because I'm
So now we're moving into what will be in Pure 2. A little bit of Pure 2, but sometimes the questions are slightly harder. So, we have to prove the difference between the squares of 2 consecutive odd numbers is a multiple of 8. And prove that x squared minus 4x plus 7 is greater than 0 for all values of x. So number 1 is more like what you would see in GCSE. Number 2 is more of what we're going to see in Pure 2. So for question 1, prove that the difference between the squares of 2 consecutive odd numbers. So 2 consecutive odd numbers, 2n minus 1 squared, and it wants the difference, and 2n plus 1 squared is a multiple of 8. Okay? So I'm going to expand out. I'm going to get 4n squared minus 4n plus 1 minus 4n squared plus 4n plus 1. So now, when I expand this out, I'm going to get 4n squared minus 4n squared minus 4n minus 4n, which is minus 8n, and plus 1 minus plus 1. Okay, now I need to make sure I factorise 8 out, so it's minus n. Okay, don't take out a factor of minus 8. No, we just want to take out the positive. Okay, 8 is a factor, therefore multiple of 8. Okay, so this is GCSE, and we should be fairly comfortable with that now. Now the second part of the question, we've got to prove that x squared minus 4x plus 7 is greater than 0 for all values of x. We've got to prove that this is a positive number for any value of x. How do we do that? What do we know is always a positive number? It could be 0 or more. Okay, what do we know? We know any number squared is greater than or equal to 0. Regardless of what that number is. If we have a negative number, we square it, it's going to be greater than or equal to 0. So, to prove that this quadratic is greater than or equal to 0, in what form do we know that we might have a bracket squared? Completing the square. Absolutely right. So, we're going to have x minus 2 squared minus 2 squared plus 7 is greater than 0. This is x minus 2 squared minus 4 plus 7 is plus 3 is greater than 0. Now what we have to do is we have to write a sentence. Okay. X minus 2 squared is greater than or equal to 0 for any value of x. Isn't it? But remember, it's specifically greater than or equal to. For any value of x, okay? And you can write that. For any value of x. Okay? Let's assume it's 0. 0 plus 3 is in fact, it's greater than 3. Okay? So therefore, x minus 2 squared plus 3 is actually always going to be greater than 3. This is because we have plus 3 is positive. Now for now, I just want you to think, this is all the logical explanations. We're going to look at how to write this completely exact. But for now, I want us to understand exactly what's going on. Therefore, x squared minus 4x plus 7 is greater than 0 for all x. So what you're going to do for me is you're going to test your understanding, and you are going to do question 1 and question 4 or 5, depending. 4 if you're okay, 5 if you're super. Okay, so identities. Now this is something that we're going to be looking into in Pure 2 as well, not only for proof but for trigonometry. We're going to learn some trig identities. This is something that always holds true. Okay, so for the first one, what values of x make the following equality hold true? 2 and negative 2. X equals 2, x equals negative 2. Okay? Then, x squared minus x equals x lots of x minus 1. Can you think of any values of x that would make this true? 3 squared is 9. Minus 3 is 6. 3 lots of 3 minus 1 is 2. Yeah, x equals 3. There could be more than one. But, for example, for the first one, x cannot equal 1, can it? For the second one, if I tried x equals 2, I'm going to get 2 squared minus 2, which is 2, and then I'm going to get 2 times... Oh, no, it does work. How about x equals 1? X can't equal 1 on the second one, because we're going to get 1 squared minus 1 is 0. No, it does. Oh. Yeah. Okay, well, anyway, there could be a few, but there might not be one. The point I'm trying to say is that an identity means for any values of x, this would be true. Okay? So this is actually an identity, because for any value of x, this will be true. For number 1, it's not true for all values of x, okay? So, in this identity, h and k are integer constants. Work out the values of h and k. So they're saying the left-hand side completely equals the right-hand side. Now, when we have identities, we always start left-hand side equals 4 lots of hx minus 1 minus 3 lots of x plus h. This is going to give me 4hx minus 4 minus 3x minus 3h. Okay, so then if I simplify this a bit more, I'm going to get 4hx minus 3x minus 3h minus 4. And on one side I can factor out an x. So x is 4h minus 3. And then I'm just going to be left with minus 3h minus 4. Now for my right-hand side, I have 5 lots of x plus k, which is 5x plus 5k. Now what I need to do is, because we know they are both an identity, I could do something which is called comparing coefficients. Oh, sorry everyone, this is a k. So, if I have a look, the coefficient of x is 4h minus 3. So that must mean that 4h minus 3 equals 5. Because we're comparing coefficients. We know the left-hand side is completely identical to the right-hand side. Okay? So 4h minus 3 equals 5. 4h equals 8. H equals 2. Then I know that minus 3h minus 4 is going to equal plus 5k. We know that h is 2. So in actual fact, I have minus 3 lots of 2 minus 4 equals 5k. 3 times 2 is minus 6 minus 4 equals 5k. Minus 10 equals 5k. K equals minus 2. So you can see here, therefore, h equals 2 and k equals minus 2. Now this is one way to do it. This is one way to solve an identity. The other problem that you could have had is if you expanded everything and moved it all to the left, you're going to have a few unknowns. And you might not have been able to work it out. So sometimes that's why we compare coefficients. So just to make this abundantly clear, so once I expanded the left-hand side, I get 4h minus 3 bracket x minus 3h minus 4. This is, okay, the coefficients must match to 5x plus 5k. That means 4h minus 3 must equal 5, because that's the coefficient in front of the x. Okay? And minus 3h minus 4 must equal 5k. Because the both sides of the equation are completely identical to the other. Because this is an identity. Okay, let's say we were to ignore the identity and we use the equal sign like we normally do, where we can move anything to either side of the equation. Okay? So, we would have... I would have 4hx minus 3x minus 3h minus 4, and then I would have minus 5x minus 5k equals 0. Well, first of all, I've got x, h and k. I've got three unknowns and nowhere to go.
That way is easier.
Yeah, it's easier to do the equated coefficients, but the reason why we can equate coefficients is because it is an identity. So, I want you to test your understanding on this question, please. Okay, so we should have got k equals 3 and h equals 6. Pardon? Yeah, the whole slide, yeah. So, what we're going to have is, we're going to have 15x minus 10, this is what the left-hand side equals, minus 3x plus 3h. Well, can I simplify this? Of course I can. 15x minus 3x is 12x. Then I have plus 3h minus 10. This is what the left-hand side equals. Fully simplified. I cannot go any further. Right-hand side equals 4kx plus 8. Again, I cannot simplify any further. Now if I equate coefficients, the coefficient of x is 12. Coefficient of x here is 4k. So that means 12 equals 4k, k equals 3. Then we have 8 on its own, so then 3h minus 10 must equal 8. 3h equals 18, h equals 6. So, what we're going to do is, homework for you is we're going to have question 1, question 2, question 3 and question 4 on slide 13. Question 1, 2, 3, 4 is also homework. Yeah, I have put the slide on Teams. Okay, Faris, you ready? I'm going to do this super quick.